Hello everyone, welcome to this 13th lecture in the NPTEL course on Riemannian geometry. So in the previous few lectures we introduced the notion of a Riemannian metric, and we saw plenty of examples, and we also saw some basic constructions regarding using the Riemannian metric. So in the next few lectures I want to introduce an important concept of how to differentiate vector fields, right. So in order to do calculus on manifolds, it's important to be able to sort of compute derivatives of directional derivatives of vector fields. So that will be the topic of interest for the next few lectures. So let me introduce this problem of differentiating vector fields. Okay, so let's say I'm given a tangent vector at a point, and let's say I'm given a vector field. Our goal is to calculate the derivative of y in the direction of v at this point P. Okay. So what would be the naive definition? So let's imagine we are in Rn. So suppose M is Rn, and let's say the vector field y is given in components by y1 yn, right. So then a naive definition would be that suppose V is also given in components by V1 up to Vn. So then a naive definition would be that this should just be the component wise derivative. So calculate the directional derivative of the kth component and multiply that by the standard kth tangent vector, right. So this would be the naive definition. In fact, this works in Rn. So this works in Rn. Okay, but on a general manifold, one could try to do the same by choosing a set of local coordinates near P. Then unfortunately this naive definition which was basically just this is not coordinate independent. Right. On the other hand, on an abstract manifold, you would like to introduce quantities that are independent of the coordinate system that you pick, right, because coordinate systems are supposed to be just a language to express something, but our eventual theory should be independent of the coordinate systems that we pick, right. So this is clearly a shortcoming. So the solution to this problem is to instead define the following. So we take the naive definition, but we introduce some correction. So this correction will be of this form. Gamma ijk yi vk, this times delta k. So if these numbers are chosen appropriately, then this is actually independent of choice of coordinates. Okay. So one thing to notice is that this correction term is zeroth order in Y. that means that it does not involve any derivatives of y. So the only derivative of y is the term that comes from this naive attempt at defining directional derivatives. The correction term does not involve any derivatives in y. So this is I mean, if I were to sort of sum up differential geometry on abstract manifolds in one sentence, it would basically be this: that differential geometry is just Euclidean geometry plus lower order terms. Okay. So this will be a theme throughout this course, that whatever sort of new notions we introduce up to first order, they will all agree with their naive counterparts in Euclidean geometry, but then in order to make sense on an abstract manifold, one has to add lower order correction terms in order to make sure that the quantity you are defining is actually invariant. So the way to do this is via this notion of a connection. Okay, and as it often happens in math, your motivation or your the reason why you want to introduce a concept is something else, but then when you study this concept, you study it using a very slick and modern looking definition. So that is what we are going to do. We are going to give a definition of connection which is completely coordinate independent. So it's a global definition of a connection, and then in the next lecture I will show how that global definition actually corresponds to something like this, correspond to this naive to this solution that I wrote down here. Okay. Alright, so that brings us to the definition of a connection. So here's a definition. A linear connection on M. So from now on I am not going to use the word linear. Whenever I say a connection, I just mean linear connection on M, is a map which is denoted usually by nabla from the space of vector fields cross itself into the space of vector fields. Okay. So this is usually denoted by this: you take a pair of vector fields and write nabla x of y. So the way you should think of this quantity is that this is the derivative of y in the direction of x or with respect to the vector field x. Okay. So you are differentiating y with respect to this vector field x. So such that you want the following properties to be satisfied. One, you want C infinity M linearity. In X, which means that for all f1, f2 smooth functions and for all x1, x2 and y vector fields, if you take the derivative of y with respect to f1 x1 plus f2 x2, then that splits as this linear combination. Okay. The second property is you want R linearity in Y, which means that for A1, A2 in R and vector fields x, y1, y2, you want the derivative of A1, y1 plus A2, y2 to simply be A1 y1 plus A2 x, y2. Okay. And the third and the most crucial property is that you want the following Leibniz or product rule. So if you take f1, f2 again C infinity functions and x, y1, y2 vector fields, then you want that the derivative of f1, sorry, let me just, because I already have linearity, let me just do it with one smooth function. Right, so then the derivative of fy in the with respect to x is precisely, you first differentiate f multiply by y plus f times this. Okay, so this is of course analogous to the product rule for usual derivatives. So let me make a quick remark that if x or y is identically 0 as vector fields, then this implies that that this is also identically 0. Okay, that just follows from R linearity in both the entries. Okay. All right, so connection is any map from a vector field across the space of vector fields to itself which satisfies these three properties. Okay, so a basic example is of course what happens on Rn. So let M be equal to the Euclidean space with standard coordinates, let us say u1 up to un, and suppose x is given in components by xi del ui, xi del I, and y is given in components by yj del j. Then one can simply define this to be so this makes this clearly satisfies all the three properties. In fact, this is just component wise differentiation, right? So this is the naive definition that I wrote down earlier. Okay, so this provides us a what we call the trivial connection on Rn. Okay. So a natural question is, do connections exist? So the answer is yes, but I am going to postpone this for until maybe a few lectures from now, because we are actually going to use the Riemannian metric to construct this connection. So one way of constructing connections on arbitrary manifolds is that you take this naive definition and glue up things using partitions of unity. But it turns out if you are given a Riemannian metric, there is a much more natural and canonical way of doing this, and I'll do this when the time comes. So I'll postpone the discussion, postpone answering this question until a few lectures down the line. But first I want to investigate some properties of this connection. So the first and most crucial property is that the connection is a local operator. So I'll label this proposition locality 1, because in the next lecture we will refine this proposition and obtain a slight generalization which I'll call locality 2. Okay, so the first, this is a two-part proposition. So let x, y1, y2 be vector fields. So suppose there is an open subset of M such that y1 restricted to u is identically the same as y2 restricted to u, then this implies that if you differentiate y1 with respect to x, then its restriction to u is the same as the derivative of y2 with respect to x. Okay, and the second part is that if x1, x2 and y are vector fields, and suppose at a single point x1 is equal to x2, then at that point the derivative of y with respect to x1 will be the same as the derivative of y with respect to x2. Okay. So in words, what this means is that if you want to compute this at some point p, then this basically depends only on the values of y in a neighborhood of p and only on the value of x at this single point p. Okay. So in terms of this y, the derivative actually takes into account how y behaves in a neighborhood of p, whereas if you are computing the derivative with respect to x, it's only important what the value of the vector at p is. Okay. Alright, so let's quickly try to prove these two. So the idea is to use bump functions. So without loss of generality, by R linearity, it is enough to show the following. Enough to prove that if y restricted to some neighborhood is identically 0, then this derivative restricted to that neighborhood is identically 0. What is the proof of this? The idea is to use bump function. So let me draw a picture. So this is M, this is some open set U. Let's say I look at a point P, I want to show that this vanishes at this P, and if this holds for an arbitrary P in U, then I am done, right. So choose some P in U, and let's take a further neighborhood V which contains P and which is an open subset of U, such that V closure is contained in U. Okay, then let chi be a bump function such that chi is identically 1 on V closure, and the support of chi is completely contained inside U. Okay, so it's a function that basically looks like this. So this is the open neighborhood V and this is the open neighborhood U. Okay, P lies somewhere here. All right, so then if you multiply chi with y, this is going to be identically 0. Why? Because y is identically 0 on U and chi is identically 0 outside of U. So chi times y is 0, which means that if you differentiate, then this is 0, right. In particular, this is 0 at this point P, but by Leibniz rule, what is this? This is chi of P times nabla times the derivative of y with respect to x plus x applied to chi at P times y at P. okay, but this quantity here is equal to 1 and this quantity here is 0, right, because firstly chi is constant near x, so any derivative of chi will automatically be 0, also y is 0 at p, so both these terms are in fact 0. So this implies that nabla x y at p is 0, okay, but since p was arbitrary, this implies that so p was arbitrary, this implies that this restricted to u is 0. Okay, now let me quickly prove the second part. So again it's enough to prove the following, that if x of p is 0, then this is 0 for all vector fields y, okay. Okay, so now let P be a point in right, so let E1 up to En be a frame for the tangent space on some u containing the point P, on some open set u containing the point P. So then I can represent my x as xi ei, where xi's are smooth functions on this open set u, right. Now let chi be as above, be the bump function from the first part, and I define the following. I let fi be equal to chi times xi on u, because xi's are defined only on u, and 0 outside, okay. Then fi is clearly a smooth, because you the support of chi is contained compactly inside contained inside u. I can if I extend this by 0 outside u, fi's will still be smooth functions on all of m. Similarly, I define ei to be chi times this ei on u and 0 outside. Then these ei's are global vector fields on M. Also, what is x? By definition, you can check that x is then simply this. Okay. All right. So now I differentiate with respect to this. So this implies that if you differentiate y with respect to x, that's just going to be this derivative, but then it's C infinity linear in this entry. So this will just be fi. So by the way, I'm again using Einstein summation convention here. So Einstein convention. So you are summing over the repeated index. Okay, so this is simply this plus 1 minus chi squared at p. So this is fi at p times this. Okay, but at p this guy is 1. So this entire thing is 0, right? Similarly, what is fi at p? Well, fi at p is chi at p times xi at p, which is xi at p, but x by our hypothesis was assumed to be 0. So these are 0. So this will also vanish. So this implies that that this is 0. Okay, so this completes the proof of the proposition. So in the next lecture I am going to use this proposition to express my connection in terms of a local frame. Okay, so that's a very useful thing for calculations, and then I am going to use that local expression to actually refine my locality theorem and prove a sort of generalization which will be useful when we discuss parallel transport. Alright, so okay, so that's it for this lecture. Thank you for your attention, and I will see you in the next lecture. Thanks.